welcome to lab number 4. We're going to be looking at filters and frequency response.
Alright, so today we're going to be building this filter circuit. This particular circuit has a capacitor and an inductor in parallel, and a resistor at the top branch, which is then going to behave like a voltage divider network with these three in parallel down there. So we know that the capacitor and inductor in parallel from our analytical work should have zero impedance at really high frequencies because of the capacitor shorting it out, zero impedance at really low frequencies because of the inductor shorting it out, and somewhere in the middle should act like an infinite impedance, which in parallel with this 100 ohm will mean only the 100 ohm is present. So then if this is shorting things out at high and low frequencies and dividing by 2 at somewhere in the middle, it's going to be a bandpass filter. And so now we're going to build it and confirm that. So we're going to go with a 100 ohm resistor from the high rail to somewhere where we can hook up a capacitor, resistor, and an inductor. So we'll go high rail up here and then connect that to maybe somewhere down here. And then we'll, at the other side, connect capacitor to ground. And another 100 ohm resistor to ground. And the trickiest part is to get the inductor in there. So we've got a 100 millihenry inductor, which this style again is two different inductors in one. So it has one inductor which goes from this pin to this pin, and another inductor that goes from this pin to this pin. And that's a little bit difficult to get onto the breadboard, so what we'll do is just put it anywhere that we can actually fit it in, and then use jumper wires to connect up to either side of it so that it's in the circuit the way we want. So we'll take one to one side of the inductor, being careful to hit the right pin, and another jumper wire from the other side to the ground. And that should be it. So then the circuit is hooked up. We can take our output by measuring at either on this side of the capacitor or that resistor relative to ground. Alright, so now we're going to hook up the scope to measure what's going on the output here. So we'll hook up from low to the output pin. Anywhere at the high of the capacitor, the resistor, or the inductor would be fine for that. And actually this is backwards, sorry. We want to hook up the ground of the scope over there and the high of the scope over on this side. Yeah. Now we also want to make sure that the scope is on the 1x, and then our channel 2 is on the same setting over there. We next need to hook up the function generator. So we've got our function generator here powered on. It's currently set to 500 Hertz, which should be around where the resonance of this circuit is from our analytical work. And we need to put it to sine wave. Then we'll hook up the ground pins, making sure the amplitude isn't too high. And when we hook up the high, then we should see something show up on the scope. So let's see. Yep. So there we go. The scope is now outputting a lot of a signal. We can zoom in to that to see the sine wave that we're outputting. And as a bandpass filter circuit, we expect that if we go to a much higher frequency, then this amplitude should drop. So I'm just going to use the top buttons here to go to increase the frequency by a factor of 10, and the amplitude is dropped on the scope. And then we'll go down by a factor of 10, and you can see if we compress things, then compared to the 1K, the amplitude has also dropped, although not quite as much as it did when we went to the higher frequency. So going down to 10 Hertz, you see the amplitude is quite a lot lower than it was. Okay, so that's measuring sort of qualitatively what's going on. You can do a little bit better with the measure menu. So what we're going to do is go to source, make sure the source is switched to channel 2, and we'll put this to channel 2. We'll need a lot of channel 2 measurements, and then we'll go to type. We can go to the peak to peak, that's going to be like our amplitude, and the frequency. Now we can't see it because the frequency is too high compared to the divisions that we're on. So you need to expand this out a little bit so that we can actually measure things. So you see we are indeed at around a 500 hertz, and the amplitude that we have is 1.34 volts. To know whether or not the gain of this is what we expected, we are going to need to hook up the output to channel 1 and compare that, because we don't actually have a measurement of the voltage that we're outputting from this scope. So I'm going to get extra probes for that. And we are back. Movie magic. Turning on channel 1, we can zero that at the same point as channel 2. We can change around the volts per division to get it onto the same scale and see what the measurement is for that. So it is reduced by, looks like roughly a factor of 2. Let's check on the measurement menu. So we need a channel 1 peak to peak. Let's put that down there. Yeah, channel 1 looks like 2.74 volts, and channel 2 1.34 volts. So we're getting pretty much our reduction by a factor of 2, our gain of 50% with the circuit at the center of the passband as we expected. Then as we go up to a higher frequency there, expanding things out, the input has stayed the same and the output has dropped. You can see a phase shift of the output now, looking like close to a 90-degree phase shift, as the impedance on the output is dominated by the capacitor. So you see we've got now that the voltage is 90 degrees behind the current, as it would be for a capacitor. And as we go to the other size scale, now the output is reduced as well and starting to phase shift into the other direction, the voltage leading the current, as we would expect for an inductive load. We can try to lower that down a little bit more and see what we're getting. So this is particularly difficult to see with the inductor, and that has to do with well, a couple of things. One is the extremely low frequencies we're getting at. As we increase the frequency, the phase shift reduces. As we decrease it, we move a little bit more to the left, so there's a good indication of that. You can see the peak of these lower signals is moved to the left. Another thing that this has to do with is the fact that the inductor is not really a perfect inductor. So this particular one that we've got in here, if you measure the resistance of the inductor, a perfect inductor would have 0 ohms impedance. This one is pretty good. It's got 2 or 3 ohms impedance, but this one, these little ones, we'll just see if we can measure that, is reading 200 ohms impedance. So for this circuit, if we were to try the same kind of a measurement with this other style of inductor, it isn't going to work nearly as well. So let's hook that up and see if we can demonstrate what's going on with that measurement. So now we're back with the other inductor, and at resonance it's behaving almost the same. You see the voltage is reduced a little bit from the voltage that we were getting past at resonance earlier. And if we go to the higher end, so the higher frequency stuff, this is behaving the same because we're capacitor dominated. That's all well and good. But as we go to a lower frequency and even lower, we don't see the same kind of drop off. So the phase shift is happening because the inductance is having a lot of is still participating, but the resistance of this circuit is impacting things as well. So on this low frequency range with these particular inductors, we don't have the same kind of signal as we would have been hoping for otherwise. All right, so one way to fix this without having to use these inductors is to try to make it so that the fact that this only drops to 200 ohm impedance at really low, 200 ohms at really low frequency, less relevant, and you might think, okay, well, we could fix that if we increase these resistors to higher than 100 ohm. And that should give you better low frequency performance. So you're changing around the circuit. Maybe if these were 10K or something, then the fact that this goes to 200 ohm is going to be basically zero compared to 10K. So here we've got some 10K resistors, and we can try out this experiment and see what happens. And this is going to introduce us to another limitation of the inductors and capacitors that we have here, and kind of explain limitations of inductors and capacitors in reality with these filter circuits. So always good to do test cases to see if they're behaving like you would expect. So again, these are 10 kilo ohm resistors. And the theory is, well, okay, if this goes to 200 ohm, then 10K should basically be infinite compared to that, so it's going to be shorting out. We'll get zero impedance if we go to low frequencies. So let's connect that back up and turn on the function generator here. And now, if we go to, so first of all, just to verify, if we go to high frequencies, then the output of channel 2 has dropped out a lot, so that's good. That part is still working. In fact, actually, we don't even have to go that high, because one of the consequences of switching the resistors to a much higher value is that this is going to change the quality factor and the sharpness of the peak that we get in the circuit. So we just have to go a little bit higher, and you can see that amplitude of the middle signal dropping off. And it also drops off as we go to lower frequency there. So even with this resistor, we can now see quite a lot of drop on either end. But something else has happened which maybe you wouldn't have expected, and that is right around the maximum gain point that we can get for this combination, which looks like it's around the 500 hertz like we were expecting. The output is only 184 millivolts to our 3.6 volt input, which means rather than 50% gain, we've got something closer to maybe 6 or 7% gain, so less than 10% gain. So that's meaning that at the maximum gain point, so the maximum of the pass band, the inductor and the capacitor together aren't combining to infinite impedance anymore. So part of the problem of this being an imperfect inductor is having that extra resistance in series with it effectively. When we have too low of a resistance here, that becomes a problem because this doesn't actually go to a short circuit at low frequency. But then at resonance, at the peak of the pass band, now it's a problem because the infinite impedance that these two in parallel go to is no longer infinite compared to the resistances that we have if they're 10K. So there's some happy medium for the resistance values to use for the particular capacitor and inductor that you use, so that your filter is going to be really dropping off to zero at low frequency and high frequency, and really giving you the gain that you would like at the center of the passband. One other thing to look for and see that we're getting non-ideal behavior of the capacitor and inductor here is where exactly the maximum gain is happening from the perspective of phase. So if these two are really being symmetric and canceling each other out, then you would expect no phase difference between the input and the output signal. However, the frequency that happens at, you see where these two are crossing the axis at the same point, is not actually the frequency where we get the maximum gain. So the maximum gain is somewhere around there, whereas the frequency where the phase is the right value is a little bit lower. So more like 387 as opposed to something like 500. So that's another indication that this inductor and capacitor aren't behaving ideally that you can look for. So we've got one more special treat right now, and the This is because the people from Keysight came by this morning, and Gap Wireless, a distributor of Keysight, has been generous enough to loan us some brand new equipment like this digital oscilloscope, so we can hook this up and see how this is doing and get experience with using some of the newer equipment. So we're going to use just channel 1, and we can modify that, move it around on the scale to get that centered. Similar controls to the oscilloscopes that you're used to, but a much faster response, much more sensitive, and much easier to do things like program. So this is a USB output. You can program this to automatically acquire measurements and save them on your computer so that you can do different analysis with this. So let's just see if we can get the triggering working. We'll go to the trigger menu and then switch. Let's see. So we're going to go source to channel 1 and push that in, and that's how we've got this switched to channel 1 now. We can go and change the time scale, and that's up here, and get a really beautiful picture of what's going on with our actual signal. So we'll have more on this particular scope and some of the stuff that it can do with different possible settings as well. So although you can use it to do exactly the same kind of measurements as we have on this other scope, why don't we see if we can do that. In fact, there are some more advanced things that you can do with this. So this also has a function generator, and we'll get a chance to play with that soon. So first we want to hook up this as well to the low and the high and see if we can get channel number 2 on there. Great. So there's our input and the phase difference that we're seeing there, so we can compare those two measurements on each scope, getting the same kind of thing. But one advantage of the color, which you never knew you wanted until you until you saw how good it could be, is right away we can see which signal is which. Whereas on the other scope, it's a little, you have to kind of remember and move it around to remember which signal was which one. So now you can see, okay, the green, and it tells you right on the display, is channel number 2. So that's all nice and good. Let's play around with the measure menu and see what other stuff we can do with that. So measure menu, we've got channel 2 peak to peak. Sure, so we've got the frequency down at the bottom, peak to peak channel 1, 1.9 volt, 3.82 volts for channel number 2. And this is interesting. So channel number 1 is measuring a 1.9 volts, whereas channel number 2 is 3.82 volts. So whereas before we saw the voltage dropping a fair bit from at our resonance, the two scopes are actually disagreeing about what the size of this signal is at the center of the passband. So this one, interestingly, is reporting 50% of the gain that we were getting otherwise. We're seeing a crossing at 373, which is a little bit different. And a peak for channel 1 looking like it's right around where we get this to a maximum of the 500 hertz that we were expecting. Okay, so the reason that this is actually reporting a different value is because of a little bit of a rookie mistake with a new scope. So this is set to the 1x probe on this channel, but the machine thinks it's set to the 10x. So we need to make sure that these have the same setting, and then change the trigger level. We can change the trigger again to go to just source channel 2 in order to get that to match. And now you see we're back at our 280, in this case, millivolts. So still a slightly different opinion about how exactly how big. Oh, now that we're on the right scale, we're getting the the right kind of measurement. So 208 millivolts measured here, 200 millivolts measured here. So on your lab day, talk to your lab tech about seeing a demo of this, and we'll demonstrate that live. There is actually a way to use this scope to generate a Bode plot directly, and it can use its frequency, its function generator on the output there to sweep around and show what the response of a circuit is directly. All right. So one last thing that's pretty fun is you may remember that the way to make a triangle wave or a square wave is by adding up a bunch of different sines of different frequencies. So the majority component of that is a sine that's at the same frequency. And so if you look at our filter here, when we put it onto triangle wave form, then you see the input is this nice triangle wave, but the output is only a sine wave. And the reason for that is the higher frequency components of this triangle wave are being destroyed by the filter. So they don't make it through, and this is now acting like a filter that's turning a triangle wave into a sine wave. And it also does something similar with the square wave. So the square wave, we're seeing out of this mostly that sine wave component. You can see the square wave needs a sine wave that's at a little bit higher. If you do the math for it, it ends up being at pi, I think 4 by pi is the first component of a square wave when you figure out the Fourier transform of that, or the Fourier series that's necessary to make up the square wave. So you see that's why when we go to the square wave, the amplitude gets a little bit higher of the 500 hertz part of it that's making it through. Okay, now the very last thing that I want to demonstrate here is something that's not using this function generator at all, and that is one of the cool things that you can do with a modern oscilloscope like this one, in particular this one again, thanks to Gap Wireless and Keysight for loaning this to us. So we've got, now, you see we've got the signals showing up again, and we can even look at this on our other oscilloscope there, if we put the triggering level to the right level. So what's happening is the function, the scope itself has a function generator, which right now is set to a very low voltage, so it's not outputting a very big signal. But you don't actually need to use a separate piece of equipment as your function generator in your scope. You can have it, you can have them all being the same, coming from the same instrument on your bench. And because it has an integrated function generator and oscilloscope in it, it's both generating the signal and measuring it with the probes. It can do some really neat things like analyze, so and generate a Bode plot by itself. Let's learn how to do that. So we'll put it on the analyze part, and then we'll change this to frequency response analysis. We'll turn that on, and then we'll just set it up here, change the signals. So right now we've got it so that the input, the one that's measuring across the entire signal, is actually our channel 2. So we'll change that to channel 2. And we set up our min frequency 20 hertz and max 20 megahertz. We can even lower that down. So actually, no, that's as low as it goes. It goes down to 20 hertz, max 20 megahertz. Let's just put it to 1 megahertz and see how that goes. Amplitude 200 millivolts peak to peak, and see how this one goes. So let's see if we can make it work now. So I wonder, did that setup stay? Yep, it seems like that that worked. And now we'll just hit run analysis and see what we get. So this is sweeping through all of the different frequencies and generating a plot there of what the output is at all these different frequencies. So you see we're getting closer to our resonance, and there's our resonance point right there. And then as we move farther away, it's dropping off. And you can see that this this inductor, as promised, is behaving a lot better. This inductor, because of its resistance, is working out as a much better filter at the high frequency where the capacitor is limiting things than at the low frequency where the inductor is limiting things. So here's our Bode plot showing a peak which should be right around 500 hertz. Let's see if we can get some cursors there. So, oh, nope. Maybe if we go to the analyze, we can get that back. Yeah, great. So let's I wonder if it will tell us what that is. So let's go to the chart and there we go. This style here will move us around. So if we go up to the top, then you see the peak is looking like it's at 501 hertz, and we've got minus 25 decibels right there. Whereas if we go over here to 1.58 kilohertz, then we're down to negative 39 decibels, quite a lot of attenuation compared to that. The lowest we can get on the low frequency is minus 33, so definitely dropping off a lot more on either side. It makes it easier to find your negative 3 dB frequencies by just looking for where we've dropped to the right range on each side. Great, and that's how you can do this analysis, both by moving around the frequency that you're generating manually and looking for your 3 dB frequencies on the scope, and a little bit of a preview of what you can do with a modern piece of equipment that's able to program and automatically sweep frequencies and measure the output.
Thanks for watching. I'll see you next time.